Okay, hello, my dear students. I'm trying to give you lectures from home because of the situation of Corona. Hopefully, everybody is fine. Today, I will speak about free vibrations, and I will give you an introduction to non-homogeneous second-order differential equations. As you know, engineers needs to find the free vibration characteristics, especially mechanical engineers, civil engineers, and aircraft engineers, as well as electronic engineers. Suppose that you have an aircraft. Okay. Okay, I'm not looking at the drawing, but I can show you this. Okay, so the wing part, you need to know the free vibration characteristic of it, such as the natural periods or natural frequencies, and also the mode shapes. Okay, so that's why you need to study free vibration, as well as also in energy. Wind energy turbines, the plates are made from this is usually very long, okay, it's maybe 50 meters or more. Okay, so you need to know this is made from a composite material with a carbon fiber, and there is of course wind, so you need to know the free vibration characteristic of the plates. And in order to prevent exciting this plate in its natural frequency, because if you excite this with its natural frequency, it will get very high vibration and may get a crashing or failure. As well as there is also an application in earthquake engineering. We speak about, of course, free vibration, okay, of objects or of structures. So suppose that you have a site and there is some building that has a high rise, for example, 30-story building, 2-story or 3-story, and this is a 1-story. Okay, and if you excite this, and of course maybe some bridges and other structures, not only buildings. Okay, so these types of structure, you should first, before you know its response against dynamic loads, engineers should find the free vibration characteristics of these buildings. You should find the mode shapes and the natural periods. So every building has its free vibration characteristics. So according to these free vibration characteristics, especially its natural frequencies, okay, and according to the natural frequency of the ground shaking, the response may differ. So it depends. So the response of these buildings against earthquakes, it may be differ according to that characteristics. So some buildings will be more affected. For example, mid-high rises buildings will be more affected than high-rise buildings during earthquakes sometimes. Okay, so it depends on the frequency content of the shaking and the free vibration characteristics of the existing buildings. That's why engineers need to find these free vibration characteristics and need to study or measure it, maybe using what we call micro-Fresnel measurements. So, in this course, because we are dealing with differential equations, usually you may simplify. So, suppose I will give you a very simple case of the suspension bridge. Okay, suspension bridge, like a Bosphorus bridge, there is 2 towers and there is a cable comes from here, from high strength material, steel, okay, and this part of the cable is anchored to the mountain here deeply. It's anchored down to the mountain, maybe it goes deep, okay, and the steel deck is hanged. This is the steel deck. You hang it by some cables. Okay. Of course, there is a continued road and there is a span. Okay. Continue. So this is the sea level. So the engineers, if you want to know the free vibration characteristics or the free vibration is actually, as we will see now, it is just a kind of a harmonic motion or a sinusoidal motion with a frequency which is related to the natural frequency of the bridge. Okay, so I want to study the vertical motion if there is no any cars on the, or there is no any traffics or trucks. What is the vertical motion of the bridge? Okay, so you may change this to the following system. Okay, if you know the diameter of this cable, you can know the cross-sectional area, and you know the length of this cable L. Okay, and you know the modulus of elasticity of the material. So A times E divided by L for each individual cable, and if you make summation of all these cables here, you can obtain the global stiffness. So you can change this system as a single degree of freedom system for approximation. Okay, and the mass, this is the total mass of the deck. I will call it M. Okay, and this is the K. So you change this to a simple system, and this will gives you a differential equation, homogeneous differential equation. And if you solve this homogeneous equation, you will find that the response is a kind of a harmonic motion. Okay, so let us see this. Of course. So this is my system. It's fixed here. You assume it's fixed here, and this is spring. You study this actually in the physics course, maybe last year. And this is the mass, and this is K stiffness. If you got this initial displacement here, and you move it with a Y, so it will oscillate along this position. Okay. So if you write the write the free body diagram for the mass, this is that you pull it like that, it will go back minus Ky. Okay, so there is only one restoring force. Actually, in reality, you should have also damping. One, we will speak about this now, after 5 minutes. Okay, so if you apply the Newton's second law for this, summation of all the forces acting on the system is equal to Ma, and you know that there is a relation between the acceleration and displacement. If I call the displacement as y, so the first derivative of the displacement with respect to time is the velocity. Okay, is the velocity v, and the first derivative of the velocity with respect to time will gives you the second derivatives of the displacement with respect to time, which is the acceleration. So I have only one force, minus Ky is equal to m times a is y double prime, second derivative of the displacement is the acceleration. So if you arrange, you'll have m y double prime plus this, and if you divide by m y double prime plus k divided by m is equal to y. Okay? So, as you see, this is a homogeneous differential, second order differential equation with a constant coefficient. So if I call this stiffness divided by my mass, I call it omega square. Okay? So in this case, if you write the characteristic equation as before, you see lambda square for this plus omega square is equal to 0. And you take this to the other side, as we show in the previous videos. So lambda is equal to plus or minus omega I. Okay? So because of that, this is a case of complex roots. So that the solution for this equation, homogeneous solution, is just a kind of harmonic motion. So the y, the solution, homogeneous solution, is equal to C1 times sine omega t plus C2 sine cosine omega t. So as you see, the solution is a harmonic function, and this is the excited or natural frequency for the system, which is equal to angular frequency, which is k over square root of k over m. Coefficient C1 and C2 can be found from the initial conditions. What is the initial velocity that you give, and what is the initial displacement you give. So the pre-vibration response is a harmonic. In real life, every system should have a damping. That function that we found it right now, it says to you that there you have a sinusoidal motion. It will vibrate for infinity. The function that is solved right now. In practice or in reality, there is no such a function that goes to vibrate without damping. Okay, there is a damping in the system or in the structures, even damping due to the air resistance. So this usually you should have a damping inherent in the material, or in the mechanical engineering system you can add a viscous damper as well. So this is a damping. I will call the damping coefficient C. Okay. So in this case, if you write the equation, you will have two forces. One is the restoring force, ky minus, and this is the c times the y prime. The velocity is in opposite direction. Okay. So if you write a Newton law, you will have just minus ky minus c y prime is equal to m y double prime. So the equation is m y double prime plus c y prime plus ky is equal to 0. So I will not solve this one, but if you solve this, you write the characteristic equation for this one. You remember it will be m lambda square plus c lambda plus k is equal to 0. And you solve for the lambda 1 and lambda 2. So if the roots are complex roots, you will have the following source of vibration. Okay. So in this case, the response again is a harmonic. If this damping coefficient is very small, if this damping value is very small, so this will vibrate. Okay, so it will be like such a. It will start from some value here, and it will vibrate. Then it will stop. Okay. However, if the damping coefficient is very high, okay, so this will not isolate. It will die directly down like that. Okay. So it will not come. It will not come to the other side. Okay. So we call it over damped. Okay. This is another topic in mechanical vibration course, so I will not enter to that, but you should know when the damping is very small, it can isolate, but when the damping is too high, it is what we call over damped, or it will not isolate or vibrate. Okay. Okay, this is all about free vibration. I will give a short introduction to the main goal in our course, which is non-homogeneous. The non-homogeneous second order ordinary differential equation. Okay. So, non-homogeneous second order differential equation, it was in this form with a constant coefficient a y double prime plus b y prime plus c y is equal to function q t. Okay. To solve this type of equations, okay, this is not anymore zero. So the solution for this, the general solution y, general solution, composed of two parts. The first part is what we call homogeneous solution, and the second part is what we call particular solution. Okay. We have solved the homogeneous solution in the previous videos. Today I will speak and give you an introduction about the particular solution. This particular solution actually is most important for homogeneous solution for engineers, what we call in mechanical engineering as a steady state solution. Okay, and this solution depends actually mainly on the exciting force or exciting input, and also on the natural frequency or natural characteristics of the system. Okay, so what does we mean by particular solution? Suppose that I have a concrete slab floor, and this a factory building or any, okay, and there is some machines here. This machine has engines, and these engines working and make some source of vibration. So it makes vibration, and due to the mass eccentricity inside the engine, this machine will exert a vertical vibration on the slab. Okay. So this is my source of acting function, which is a Q here, and it has some vibration frequency. I will call it omega 1. Okay. So the machine is hitting on your floor, for example, by 7 Hertz. Okay? So, and you study the vibration characteristic, free vibration of the slab. The slab has suppose that this is 7 Hertz, for example. Okay? It's actually not omega, this is a frequency F. Okay? Because there is a relation between that. The frequency of this machine is 7 Hertz, for example. Okay? And the frequency of this is, for example, 2 is equal to, for example, 2 Hertz free vibration. So I am looking for, in my course, what is the y of t, what is the deflection, how vary with respect to time. Okay, so if you put a sensor here, an accelerometer or a velocimeter, okay, and you measure this vibration, you make experiment and you measure that, and then you see the frequency content of this, you will find the main one is the most important one for you is 7 Hertz. It means that your slab will move with the machine, okay, it will vibrate with a 7 Hertz. Okay, so you act on it with 7 Hertz, it will vibrate with a frequency of 7 Hertz. However, the amplitude of this vibration is not the amplitude as the exciting force, as you will see. So this is an important the particular solution part actually depends on the characteristics of this. So the particular solution part, you will have a sinusoidal, for example, function that works with 2 pi f. F is 7 hertz here times t. Okay, so you have a sinusoidal function if this is actually sinusoidal excitation, and it will vibrate with the same vibration of that exciting force. Okay, engineers, you should avoid a position that if the free vibration characteristic, for example, of this is, for example, 7.5, and you apply a force to the 7 and 7.5 are so close to each other. So you should avoid this situation, because if the exciting force vibration and the natural vibration of the slab is close to each other, you will have too much high vibrations, and we call this resonance. So we should avoid such a thing. Okay, so 7 and 3 are away from each other, so the response is not that much, and there is not too much deflection if such a case happens. Okay, so this is what I speak about, particular solution, and this is what we call a steady state solution, because the machine is always there and always vibrates, so it will not stop. Maybe it will work for 4 hours. So the solution here we call y homogeneous plus y particular. If you draw it, there is a homogeneous solution like this. In the beginning, maybe it will stop here, but the particular solution is a kind of sinusoidal with 7 hertz, for example. Okay, so if you add this to that, both of them will have in the beginning some, you will add these peak to these peaks, so you have some like this. Then after a very short period of time, maybe 5 seconds or 7 seconds, okay, you don't know, it will be the steady state solution, or the particular solution will control. So the particular solution is very important than the homogeneous solution. Okay, so there is several ways to find particular solutions in this course. There is an undetermined coefficient method, there is a variation of parameter method, and there is a Laplace transform method. Next lecture, next video, please follow me, and I will give you lectures about how to find a particular solution using these methods. Thank you for watching, and have a nice day.